The total differential is a way to express the change in a function. It's made up of more than one variable. So for instance, if f is made up of x and y, then the change in x, the change in f rather, is going to be a function of the change in x and the change in y. What also matters is the slope, how rapidly f varies with x, and how rapidly f varies with y. So in both cases, we're multiplying a slope by a change to get how much the change in f due to y is, and the slope and then the change in x to get how much of the change in f is due to x. And we put them together, we get the total change in f. This is kind of like if you imagine maybe looking at a map, and we can walk in two different directions, and the map is a map of a mountain, and the mountain is really more of a ridge, right? It's not a symmetric mountain. And if you were to walk north from the peak, you can see there's a very, very steep slope. And so for a given distance, you're going to go quite far down. On the other hand, if we go east, we see that there's a very gentle slope. Now, in reality, we might find it's more likely that what we do is sort of a combination, that we'd move both north and east. In that case, there'd be, if we wanted to know how far down we went, we would use an equation just like this one up here. We'd multiply the slope in the north direction by how far north we walked, the slope in the east direction by how far east we walked. Okay, and this is a general principle. If we have a function that has 3, 4, 5, 6, or even more variables, we can just keep adding terms to the total differential. Let's go to the next page. Let's apply this to a concrete situation. Let's look at the total differential of internal energy. So we can write the internal energy as being composed of two variables, temperature and volume. And so take a minute to think about how you'd write the total differential for this. Okay. Okay, maybe you already have it written out in your own notes. Okay, so you should have something like this. Change in U with T. Oops, I didn't leave myself much room for the dt, did I? And the change in U with V. Okay, so you should have something like that. Great. Now that's a little bit of a cumbersome statement, and so what we do is we give these things names. Okay, so this term we call C sub V because it's constant volume, and we call it the constant volume heat capacity. Oops. And you may have heard of CV before, or you did hear about CV before in physics class. And similarly, this partial derivative is also named. We call this one pi t. And the name for that is the internal pressure. If you do a little unit analysis, you'll see that to get units of energy, which we need for internal energy, that pi t has to have units of pressure. Okay, very good. Now, this means that in general, we can write a general expression for the change in internal energy for any process. We can see that we've got to have a CV term, which is dependent on temperature, and a pi t term that's dependent upon the volume. And one thing that's really useful to know about pi t is that for ideal gases it's equal to 0. But we have to be careful. There's a tendency to forget that it's not 0 for everything else. So you might want to underline that that's for ideal gases only. Okay. For every other case, we're going to have to worry about that PV, that dV term. All right, moving on to enthalpy. You should be able to do a total differential for this. I will give you that it's conventional to say that enthalpy is a function of temperature and pressure. Right? We'll see later that this is a very convenient definition. For now, just accept that. So go ahead, take a minute here to write out an expression for dH in terms of T and P. Okay. All right, so we have the change in H with T. And we have the change in H with P, pressure. Okay, and as you probably guessed, both of these are named partial derivatives. This is the constant pressure heat capacity, and this is called mu T. This is the isothermal Joule-Thomson coefficient. And because there's actually another Joule-Thomson coefficient, so you should get in the habit of saying isothermal Joule-Thomson coefficient. And this, of course, is the constant pressure heat capacity. Okay, and mu T is actually equal to 0 for ideal gases, just like pi T. Let me point out that later on, we're actually going to prove that it's 0 for ideal gases. For now, let me just justify it by telling you that if you have an ideal gas, it has no intermolecular forces, and so I think it makes sense that the energy of the system doesn't change just by virtue of changing the interparticle separation because there's no attractions. On the other hand, we know that this term should not be 0 for ideal gases or for anything really, because if you're at a higher temperature, you remember that the molecules are moving faster, and so they're going to have more kinetic energy, and that feeds into both the internal energy and the enthalpy.